You press a button. Up, down, that's it. That's the entire interaction most people ever have with an elevator. But somewhere behind that wall, inside a steel shaft you will never see, a machine is making a decision. Which car goes where? Which floor gets served first? Which person waits 30 seconds? And which person waits 4 minutes? And in a tall enough building, that decision is being made by an algorithm doing more math per second than most people realize exists inside a box that just goes up and down. Sounds simple? It is not simple. And the story of how elevators actually decide where to stop is one of the strangest, most invisible optimization problems in the entire built world. Here's the thing about elevators that almost nobody thinks about. A single elevator car is not smart. It's a box on a cable. What's smart is the system deciding what that box does next. And that system has to solve a problem that sounds easy, but is actually brutally hard, called, in engineering terms, the elevator dispatch problem. Picture a 50-story office tower. 8 elevator cars, 9 in the morning. 300 people are trying to get from the lobby to their desks in the next 20 minutes. Every one of them wants to go somewhere different. Every one of them wants to wait as little as possible. And every elevator car can only be in one place at one time. Multiply that by every floor, every direction, every person who might press a button 2 seconds from now that nobody can predict yet, and you have what mathematicians call a combinatorial explosion. There are more possible ways to route those 8 cars than there are seconds since the building was built. No system checks every possibility. It can't. Instead, it has to guess, fast and guess well. That's the whole game. Speed of guess versus quality of guess. And the history of elevator dispatch is really the history of getting better at that guess. Before computers were cheap enough to put inside every elevator bank, buildings used something called collective control. This is the system most people who grew up before the 2000s actually experienced without knowing it had a name. Here's how it worked. Every car followed a simple rule. Keep moving in your current direction, serving every call along the way until you run out of calls in that direction. Then reverse. Think of it like a bus that never stops running its route. If the elevator was going up and someone on floor 12 pressed the up button, the car would stop. If someone on floor 9 pressed the down button while the car was going up, the car would ignore that call until it turned around and came back down. This is why, if you've ever stood in a lobby and watched an elevator go up, then stop 3 floors above you, then keep going up even further before finally coming back down to get you, that wasn't a malfunction. That was the rule working exactly as designed. The car had a job. Finish the trip you're on before starting a new one. Collective control was clever for its time because it required almost no computing power. A few relays, a few switches, that's it. But it had an obvious flaw. It didn't know anything about the people waiting. It didn't know how many people were on floor 9. It didn't know if the car was already packed to the ceiling. It just followed the loop. Everything changed once buildings could put real computing power behind the elevator banks, starting seriously in the 1970s and accelerating through the 80s and 90s. This is when companies like Otis, the same company that put the safety brake into elevators back in the 1850s and made tall buildings physically survivable in the first place, started building what's called dynamic dispatch, or sometimes conventional dispatch. Here's the shift. Instead of a fixed rule like finish the loop, the system now asks a question every time a call comes in. Which available car can answer this call with the least added delay to everyone already being served? This sounds obvious once you say it out loud, but it required the system to track something it never had to track before: the future. Not literally predicting the future, but estimating it. Where will each car be in 10 seconds? How many stops does each car already have queued? How full is each car right now based on weight sensors in the floor of the cabin? All of that gets fed into a constant recalculation, happening every time a new button gets pressed anywhere in the building. This is also where a strange little detail comes in that most people never notice. The weight sensor. Every elevator car has one built into its floor, and it's not just there to stop the doors from closing on an overloaded car. It's also feeding data into the dispatch algorithm in real time. A car that's already near capacity gets deprioritized for new pickups, even if it's technically the closest one. The system would rather send a slightly farther, emptier car than cram 3 more people into a box that's already full. You probably experienced this and thought it was random. It wasn't random. It was the weight sensor talking to the dispatch computer. Now, here's where it gets genuinely strange. And this is the part almost nobody outside the elevator industry has ever heard of, even though most people in a modern skyscraper interact with it every single day without realizing it. At some point, engineers realized the old up and down button in the lobby was actually the bottleneck. Because think about what that button tells the system. Nothing. It tells the elevator you want to go up. It doesn't tell it you're headed to floor 31 specifically. The system doesn't find that out until you're already inside the car and you press the floor button yourself. By then, the decision about which car should have picked you up has already been made blind. So, starting in the 1990s and accelerating hard through the 2000s, a new system appeared called destination dispatch. You've almost certainly used one if you've been in a modern office tower, a hospital, or certain hotels, and maybe assumed it was just a fancy touchscreen for no reason. It's not decoration. It's a completely different algorithm underneath. With destination dispatch, you don't press up or down in the lobby. You type in the actual floor you want before you ever get in a car. The system sees in advance every single destination every single person wants, and only then assigns you to a specific car, usually announced on a screen, something like Car C. People headed to similar floors get grouped into the same car. People headed to wildly different floors get split across different cars entirely. The math behind this is where it gets close to genuinely elegant. Instead of reacting car by car to random calls, the system is solving something closer to what's called a bin packing problem. The same category of math used in shipping container logistics and airline seat assignments. It's grouping a scattered set of destinations into the smallest number of trips, weighted by time, not just head count. This is one of the reasons a system like Otis's Compass, or Schindler's Port Technology, or KONE's Polaris, can move noticeably more people through a building in the same amount of time using the exact same physical elevator shafts and cars that existed before. Nobody added a new elevator. The building didn't get bigger. The algorithm just stopped wasting trips. Buildings that installed these systems have reported handling significantly higher passenger volume during the exact same morning rush without adding a single new shaft, purely because the routing got smarter. In a super tall tower, where digging a new elevator shaft after construction is essentially impossible without gutting the building, that math is the difference between a functional skyscraper and a lobby full of furious people at 9 in the morning. Here's a detail that almost nobody thinks about until you say it out loud. In a tall enough building, the elevator itself becomes a real estate problem, not just a transportation problem. Every elevator shaft takes up floor space on every single level of the building, all the way up. In a very tall skyscraper, if you tried to serve every single floor with a single bank of elevators running from the lobby to the top, you would need so many separate cars and therefore so many separate shafts that the shafts alone could eat up close to 40% of the building's total floor area. That's not a rounding error. That's nearly half the building turned into empty shaft space instead of office space or apartments. This is why super tall buildings like the Burj Khalifa, currently the tallest building in the world, or One World Trade Center in New York, don't run every elevator from the ground floor to the roof. Instead, they use what's called a sky lobby system. You take one express elevator from the ground floor straight up to a transfer floor partway up the building, sometimes called a sky lobby, and then you switch to a second local elevator bank that only serves the floors in that upper section. This sounds like an inconvenience, an extra step, one more elevator to catch. But it's actually a dispatch optimization at the scale of the entire building. By splitting the building into zones, each elevator bank only has to solve a much smaller version of the dispatch problem. Fewer floors to consider, fewer possible destinations, faster decisions, smaller shafts, more usable floor space per level. The Burj Khalifa uses this exact zoning strategy, and its express elevators are also among the fastest passenger elevators ever installed, because an express run with no intermediate stops is the one case where the dispatch algorithm has almost nothing left to decide. Go up, don't stop, arrive. Here's a question worth sitting with for a second. What is the algorithm actually trying to minimize? Most people assume the answer is simply wait time, how long you stand in the lobby before a car shows up. That's part of it, but it's not the whole picture. And the parts people miss are the interesting part. Modern dispatch systems typically balance at least 3 competing numbers at once. First, average wait time, how long before a car arrives to pick you up. Second, average travel time, how long the actual ride takes once you're inside, including every stop the car makes along the way to drop other people off. And third, something called handling capacity, essentially how many total people the whole system can move per 5-minute window during the busiest rush. These 3 goals actually fight each other. If you optimize purely for the shortest possible wait time, The smartest move is often to send a car immediately, even half empty, the second anyone presses a button. That feels great for the person who just pressed the button. It's terrible for total building capacity because that car makes far more trips carrying far fewer people each time, wasting the one resource that's actually scarce, which is total elevator seconds in the building during rush hour. So real dispatch systems are constantly trading a little bit of your personal wait time against the overall throughput of the entire building. Sometimes the algorithm makes you wait an extra 15 seconds on purpose because it's about to consolidate you with 4 other people heading to nearby floors, and that trade genuinely moves more total people through the building over the course of the whole morning. You never see this trade happening. You just experience it as for some reason that elevator took a little while today. And here's the part that almost never gets mentioned. The moment when this entire elegant system breaks down. Fire alarms. The second a fire alarm activates in most modern buildings, every single dispatch algorithm described so far gets thrown out immediately. Elevators are programmed to override all of it, return directly to a designated floor, usually the ground level, open their doors, and go completely out of service for passenger use. This is called fire service recall, and it exists because elevator shafts can act like chimneys during a real fire, and because power to the cars can fail unpredictably in an emergency. All of that carefully tuned bin packing math, all of that sky lobby zoning, all of that weight sensor prioritization gets deleted in an instant by a single hardwired rule that beats everything else. Get the cars to the ground and get them there safe, empty, and out of everyone's way. It's a strange kind of humility built into the system. All that computing power, all that optimization, and the most important rule in the entire building is the simplest one, which is, in its own way, a pretty fitting place to end. The smartest elevator system in the world still knows exactly when to stop being smart.